Since S is almost injective, only C terms in the sequence S equal to S1, S2, etc. can be equal to 0. And each non-zero absolute value in S can occur at most 2C times. Remember, we might assume that C is an integer. By the definition of almost injectivity, we know that there exists C such that each value in the sequence, which could be positive or negative, can only occur at most C times. For zero value, it can occur at most C times. For non-zero value, we'll take the absolute value of elements. It can occur at most 2C times, because we are combining the positive or negative values. So there'll be at most 2C times. So we get the upper estimate for the number of elements, the number of distinct absolute values. And now we are going to give a lower estimate, and hopefully this lower estimate will contradict to this upper estimate, and that contradiction will finishes the proof. So we are still estimating this guy. And you do have a lower bound. So what lower bound can you get from the information here in this paragraph? You get this is bigger or equal to n minus c divided by 2c. So if you look at this lower bound and this upper bound, you compare them when capital N is very big. First of all, this will tell you that this number, this upper bound, is always bigger or equal to the lower bound. And the next thing you want to do is that you want to take the logarithm of both sides. So say you take log base 2 of both sides, because this is the power of 2, so you might want to take the log 2. This gives you the logarithm base 2 of 2 raised to the power f of capital N plus 1 is bigger or equal to 1 over k times the logarithm of n minus c divided by 2c. But now if you look at the left hand side, this guy, in order to use the base 2, you want to majorize this guy to 2 raised to the power f of n plus 2 raised to the power f of n, which is simply 2 raised to the power f of n plus 1. And this is equal to just f of n plus 1. So now you get this guy is bigger or equal to this for any n large. But this would be absurd, because if you divide both sides by log base 2 of capital N, the left hand side is bigger or equal to 1 over k times log base 2 of this divided by log base 2 of n. By the elementary calculus, we know the right hand side, we have the limit 1 over k. But the left hand side, by our assumption that, remember, f of n divided by log base 2 of n equals 0 as little n goes to infinity, so the left hand side will converge to 0 as capital N goes to infinity. So because k is a fixed number, when capital N is large enough, you get the contradiction that n is bigger or equal to 1 over k, that 0 is bigger or equal to 1 over k. So this will be a contradiction. And this contradiction finishes the proof. By the way, in case you don't see it, let me quickly explain why Elsholtz theorem implies the Schur's theorem, so that you know that over 100 years, there's really some substantial progress on this problem. If you fix any non-constant polynomial p of x, and you consider the set of values of this polynomial on the set of positive integers where this polynomial is non-zero, and you arrange this as a sequence, the set S will be almost injective. That is because for any constant c, p of n equal to c only has finitely many solutions in terms of n with respect to n. In this situation, every value of the set S occurs at most d times, where d is the degree of this polynomial. That is because, by the fundamental theorem of algebra, any polynomial of degree d has at most d many solutions. So every value of this polynomial can only occur at most d times, given the fixed polynomial of degree d. So this set will be almost injective. Now, why the set S of sub-exponential growth? How would you take f, a function f, from set of positive integers to positive real numbers? What you do is that you consider if the degree of p of x is equal to d, say p of n equals 0, has L, where L is less than or equal to d, distinct solutions in N denoted N1 less than N2 dot dot less than NL. Then for sufficiently large little n, because we consider S, we skip those values where p of n is equal to 0. S of n will be equal to p of n plus L. If you want to make this more specific, I think this happens when n is bigger than n sub L. So now you know that S of n will be a polynomial, will be the value of polynomial p at the integer n plus L for any n greater than n sub L. Now, let us consider the absolute value of S of n. This guy will be equal to 2 raised to the power 2 raised to the power log base 2 of log base 2 of the absolute value p of n plus L. And this part will be a function f. You know, log 2 of this divided by log 2 of n will go to 0 as n goes to infinity. Just by calculus. This p of n plus L will be bounded by some power of n for large n, and you can move that power outside, and we'll take the logarithm twice. The growth rate will be slower than when you take the logarithm just once. So this quotient will go to 0 as n goes to infinity, if you take f to be this power index. And that is why S in this special case of polynomial has sub-exponential growth. Actually, when you take this S, you don't have to choose those polynomials whose values is non-zero. You can include zeros in here. In that case, its conclusion will be trivial, because there are infinitely many different primes that divide 0. That case would be trivial. That might be why Schur want to exclude that case from this theorem. And you might also be interested to know why I said infinitely many proofs in the title. of this video series. That is because Elsholtz theorem, or in particular Schur's theorem, tell us there exists infinite many such that P sub s is infinite. Because P sub s is infinite implies that the set of all prime numbers is an infinite set. So each non-constant polynomial P of s with integer coefficients will provide a proof for the fact that there are infinite many primes. That there are infinite many proofs really refer to the fact that there are infinite many polynomials that are non-constant with integer coefficients. But you might want to just take this as a joke, because we just gave one proof due to Elsholtz. And that idea is just one idea, which cannot really be counted as infinite many proofs. So that's it.